All right, let's talk about the different factors that affect solubility. So how much of a solute will dissolve in a particular solvent? The three main factors are structure, temperature, and pressure. By structure, we're talking about things like polar and nonpolar. So polar things dissolve in polar solvents, nonpolar solutes dissolve in nonpolar solvents. Also temperature, and there's different rules depending upon the solutions. So more often than not, raising the temperature makes something more soluble. If we want more sugar to dissolve in water, we heat the water up. However, that's not always the case. There are some solutes that actually dissolve better in colder solutions, and we'll look at some of those. And then also pressure. This doesn't apply to solids. Okay, if we put water under high pressure, it's not going to dissolve more salt, but it applies to gases. And so if we pressurize carbon dioxide over water, we get more solubility. That's why when we make soda pop, we close the bottle off so that the pressure stays high inside there, and it keeps it from going flat. So here's an example of two different substances that are water soluble. And they're water soluble because of these little guys right there. So those hydroxyl groups form hydrogen bonds with the water. And since they can form those hydrogen bonds with the water, that means water is going to be attracted to it, surround it, and cause it to dissolve. Glucose, which is a form of sugar, same thing. Look at all those different hydrogen bonds it can form. Those different hydrogen bonds are going to cause it to dissolve in water. And both of these right here, I want you guys to recognize now that they're not going to form electrolytes, which means they're not ionizing. Something like sodium chloride, the reason that dissolves in water is because it breaks apart into Na plus and Cl minus, and then the water molecules can be attracted to the cation and the anion, causing it to dissolve. These guys right here, though, are not ionizing, so it's not breaking apart into pluses and minuses. It's completely different. Neither one of these will conduct electricity when they're dissolved, and it's because they don't ionize, they don't form electrolytes. Those of you who take vitamin C supplements, it's good for you. It helps your immune system. It's actually best to take your vitamin C at different spaces throughout the day, and it's because of solubility. So if you take all of your vitamin C in the morning and you drink a glass of water, day goes on, you go to the bathroom, and guess what also comes out along with the urine? That's right, your vitamin C. Since it's soluble in water, it flushes out of your system. And so it's actually best to take a little bit in the morning, take a little bit in the afternoon, and a little bit in the evening. That way it's constantly staying in your body. Taking it all at once is actually not that great for you. And it's also why if you look on the back of your vitamin C supplements, it's going to say the percent daily value that you take with one of those pills is like 1,000% of what you need. And it's because you're just influxing your body with it because you know it's going to flush out later. And so you can take plenty of it, and you can't really overdose on vitamin C because it doesn't dissolve anywhere else in your body, just in the liquids, and it flushes out pretty easily. Other vitamins like A and E that are fat soluble because they are non-polar are actually bad to take too much of because it'll dissolve in your fats and build up there and eventually kill you. You can overdose on those too. Then, of course, chromatography, which helps us see how polar or non-polar a particular substance is by looking at how far it travels with a particular solvent. So thinking of Le Chatelier's principle, this actually has to do with solubility and temperature, remembering that a saturated solution is at equilibrium because there's a little bit of solid left at the bottom. And so if we've got that little bit of solid at the bottom and we add more heat to the solution, turns out that most solubility is endothermic. So when we add heat to it, it's going to cause equilibrium to shift away because if things get hot, it's going to move away from the heat in order to cool itself back down. And what that does then is it moves towards the side with the ions, and so it's going to just cause more of the solid to dissolve. And that's why heating up a solution typically causes more solute to dissolve. However, as we saw with the hand warmer lab, some salts actually produce heat, so they're exothermic when they dissolve. So if you heat these solutions up, if you add heat to it, that's going to cause equilibrium to move away from the heat. And if it moves away from the heat, it's shifting back towards the reactants, which is solid. And so this is actually going to cause less solubility, and it's going to cause it to precipitate out. So we'd end up forming more solid at the bottom. So here's a solid solubility and temperature chart, and what this shows is the solubility, so it's the grams of solute for every 100 grams of water, and then the temperature. So we see potassium nitrate has got the most distinct difference. As you heat the solution up, you see that it becomes more and more soluble. And so, at 100 degrees, it looks like you can dissolve about 185 grams per 100 grams of water, as opposed to at 10 degrees, maybe 10 grams per 100 grams of water. And you can see with potassium sulfate, potassium nitrate, and sodium chloride that the solubility increases as you increase temperature. However, with the cerium sulfate, cerium 3 sulfate, notice how this line actually drops. That means that its solubility decreases as temperature goes up. So that must be an exothermic process for dissolving that particular salt. So real quick sidestep into fractional distillation, because this is going to be an important lab concept that might appear on the test. So fractional distillation is when we have a liquid-liquid solution. So multiple liquids combined together, they're going to have different boiling points. And so then if we take a solution, so this would be our mixture down there, and we boil it, they're not all going to boil at the same time. So if we think of like methanol and water dissolved in each other, methanol's got a boiling point, I believe, at about 80 degrees Celsius or 85, whereas water is 100 degrees Celsius. So if we were to mix those together, and we would typically have a thermometer in here as well. My thermometer's a little bit off, sorry. And that's going to tell us what the temperature is at the particular time. So we heat this up. Once it reaches 80 degrees, we would see our thermometer read 80 degrees, and we would notice some vapors coming off. Those vapors coming off would not be water. Water doesn't boil at 100 degrees Celsius. It would be our methanol. And so it would vaporize, and then it would condense up here, roll down this tube, and collect down there. And so what we would collect first would be the methanol. Eventually we would see that temperature rising again, and that would eventually get to 100, start boiling again, and then the water would come off. But if we would cut it before it was able to rise above 80, we could collect a pretty pure sample of methanol down there. Now there would be some water trapped in with it, but we could actually take this condensate, distill it again, and generate eventually a pretty pure sample of just straight up methanol. So this is an important laboratory technique for generating or purifying samples of liquid-liquid solutions.